Hi, I'm Matt, obviously. So I always like to start with this quote because it's something that's sort of, bandied around a lot nowadays on Stack Overflow and various forums and what have you. And it's generally sort of used as a way of essentially, hammering on newbies for thinking about optimization. And it's usually used in the context of saying micro-optimization is bad and this sort of thing, and you shouldn't be thinking about optimization at all. You should let the compiler do it. Whereas in its original full quotation, what it's actually saying is, yes, you should optimize, you should think about optimization, you should think about micro-optimization as well, but you should be wise about how you optimize and where you're optimizing. You should optimize the 3%, but you should do that after you've identified where it is. So about 12 years ago or so, I couldn't walk for about 10 minutes without having to lie down for a couple of hours afterwards. So the concept of efficiency and performance has a slightly more real-world, perhaps personal quality for me than it does for maybe a lot of you. And I tend to see it more externally than solely within computer applications and whatnot. For example, Google Maps, for example, is a good example of sort of computers and real-world efficiency coming together. You've got all sorts of things like image compression, network compression, browser efficiency, JavaScript efficiency, all these different sort of things coming together to increase this real-world efficiency. If you think about the millions, maybe billions of liters of petrol that the app has saved since its inception, not to mention driving time, user frustration, wear and tear, all that sort of thing. Now, the only reason I'm saying that is just to illustrate that what we do as computer programmers does make a difference in the real world, and sometimes that's not very visible. And that's why conferences like this are quite good, because they bring all of us together in a way that we can see each other's efforts and that sort of thing. So, a little bit of background about myself. Yay, programmer jokes. Am I right? So, started programming quite early, got my BSc when I was 21, programmed in some legal publishing firms and then quit out of that to have a long-term illness instead. And then about 3 or so years ago, I wanted to get back into programming. Specifically, I wanted to make some games. And I decided I wanted to write my own game engine because why not? It should only take a couple of months. So 1 year later, the game engine is finished, and obviously I've learned a lot in the meantime because it had been about 10 years or so since I touched C++, and obviously a lot has changed. And the first thing I did was I went through all the open source game engines that were available and kind of looked through what they were doing, and I kept on coming across this thing called Vector. Now you've got to remember that when I completed university, the standard library was kind of a thing, but nobody was really using it. It wasn't that much of a thing. So we learned how to make linked lists, not how to use them. So this thing Vector, I kind of went, oh, this kind of looks like an extensible array of some description, looks like it could be very useful for games. No, actually, kind of not really. Why is that? And any game programmer here will know sort of some of the workarounds that we have for dealing with Vector, but just for the sake of argument, I'll go over what are the problems with Vector in its default state. So, crappy erasure performance for large amounts of data. Even if you're using erase-if, then you get per-frame jitter. Or even if you've got small amounts of large data, so large elements. Poor insertion performance if you're inserting on the fly singly. Insert invalidates all your pointers and iterators. It doesn't invalidate indexes. Erase invalidates pointers, iterators, and indexes to all elements after the erased element. And it requires a single contiguous memory block, which can be problematic depending on your RAM limitations in your system and that sort of thing due to fragmentation. So why are all these things problematic for games? Well, to go into that, we first have to analyze what is game data in general, because it's not quite the same as other domains. So this is stuff that I've garnered A, from my own experience, B, from talking to other developers, C, from talking to the SG14 group, and it seems to be relatively consistent. The first thing is that elements within containers tend to utilize elements within other containers. Doesn't matter whether you're talking about a flat C-style array or a vector or whatever, things are going to refer to other things. So if you're a game programmer, you already know. If you're not, then with most games nowadays, there's some sort of entity component system, usually combined with a little bit of OO. And so you might have your base level object, an entity, and it refers to, say, a sprite and then a sound and so on and such forth. And you're going to have multiple instances of various different kinds of things, like walls or enemies or whatever. So you're not going to want to have those resources within the object itself. You're going to want to refer to them, otherwise you waste memory, etc. So any container or use of a container which invalidates kind of your linkages between containers is not going to fly. By the way, throughout this talk, I'm going to be using the term links just as a shorthand way of saying iterators / pointers / indexes, basically whatever you're using to get one thing to refer to another. Order is unimportant for the most part, so generally we've just got data, we iterate over it, transform it, this refers to that, we bring in this, stuff goes out to the screen and magic happens and we have a game. Small to medium-sized classes and structs are the norm, not scalar types. Obviously, if you're using a structive array configuration, that's the exception. By the way, obviously, this isn't all game data. This is just kind of the bulk majority of stuff. Can't generalize too much. Erasing or otherwise deactivating objects in real time is common. You kill an enemy, you destroy a wall, that thing no longer needs to get kind of iterated over. And creating new objects and adding them into a game in real time is also common. So spawning things, for example, if you have a memorpaga, then player pops into an area and you have to add stuff in there. So basically having some kind of extensible container is useful. More stuff. We don't always know in advance how many elements there will be in a container pre-development or necessarily during play. Again, for during play, the memorpaga example is good because you don't know how many players there are going to be in a particular area, and that affects the number of creatures and what have you. Pre-development, that's pretty obvious. I mean, as you work on a game, you're refining things, you're taking stuff out, you're putting stuff in, etc. The number of objects that we tend to have in games is not what you tend to see on online benchmarks, so 1 million integers or whatever. So for a typical indie game, you could be looking at maybe 100 to 1,000 objects per level. If you're talking AAA, then I think Mike Acton said Sunset Overdrive used about 84,000 objects per game level. For performance reasons, memory storage, which is more or less contiguous, is preferred. I think everybody's gone over this enough in previous CppCons that I don't need to go into it in great detail, but the usual story, RAM speeds have gone like that, CPU speeds have gone like that, and we've got this slightly ever-widening gap between the two, which means that we can get approximately 200 instructions done in the same time as it takes to fetch one integer from main memory. So the name of the game is to get everything into the cache, and the best way of ensuring that everything is in the cache is to have it contiguous in memory. Speaking of which, memory usage and constraints are often critical considerations. So if you're on a closed platform, that's obvious. But even if you're on PC, you don't know how much memory the end user is going to have, and you don't necessarily know how much RAM they've got left, what other applications they've got open, etc. And the last point is that we generally don't want containers which allocate upon initialization. We want them to allocate upon first insertion. So an example of how this could be problematic would be something like a quad tree, using that for collision detection. And for those of you who don't know, a quad tree tends to be made up of nodes, subnodes, sub-subnodes, etc., etc. And each of those nodes can contain collision blocks, or it might not. So it may just contain subnodes. So if you're using something like libstandard C++'s deck implementation, which allocates upon initialization, then every time you allocate a node, it's also going to allocate another chunk of memory for the deck, regardless of whether or not that memory gets used. So you lose memory, but you also lose performance because allocating memory is problematic. So what are some of the more common vector workarounds? There's a whole bunch of them, but I just thought I'd go into a couple. Now, I think Chandler Carruth is going to be going into a few of them during his talk, so might have to eat my hat after that one. Anyway, first one, using a Boolean flag or something similar to indicate that something's been erased. For both of these, we basically have to use indexes to refer to elements within the container, because pointers will get invalidated upon insertion. But using a Boolean flag to indicate erasure, the good thing about this is that it's really fast to erase. The bad thing about this is that it's actually quite slow to iterate over the data, and I'll go into why that is in a second. Might just up my lapel mic. Second one, using a vector of indexes referring to a vector of elements. So you've got your elements, 10 of them, and then you've got your vector of indexes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you erase from the vector of indexes, not the vector of elements. And then when you iterate over the vector of indexes to access the elements. So say you want to erase element 4. So you get rid of that in the vector of indexes. So it's 0, 1, 2, 3, 5, 6, 7, 8, 9. And then when you iterate over the data, it just skips element 4. So the good thing about that is that it's relatively fast for iteration. The bad thing about it is that it's pretty slow for erasures because you still get that reallocation cost whenever you do the erasure in the vector of indexes. Neither solution frees up memory to the OS. So if you keep on inserting into and erasing from on the fly, then you're going to get a gradually increasing container size. And both of them, of course, have relatively slow singular insertion on the fly speeds. So the alternative that I've been working on for the past couple of years, an alternative of many, definitely not saying it's the only alternative. It's an unordered container. It's under a permissive zlib license, which basically means you can use it for whatever, you can modify it, blah, 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 so long as you don't pretend that you wrote it. It never invalidates pointers to non-erased elements. It reuses memory from erased elements and frees them to the OS. Performance is geared towards small to large classes and structs rather than scalar types. And in the context of all those game data requirements, it's faster than any unmodified standard library container. And I'll go over what its performance is like compared to the modifications in a little bit. So, what is its sort of abstract design? Uses multiple memory blocks, which prevents element pointer invalidation upon insertion. The blocks are freed to the OS if they become empty. The blocks must be removable with low performance cost and without pointers to elements being invalidated. So, for example, we couldn't use one way of implementing a deck, for example, is to have a vector of memory blocks, and we couldn't do that because when you got rid of one of the memory blocks, all of the other memory blocks would reallocate, so you get reallocation cost, and also you get those pointers being invalidated. It also records all the erased elements in a skip field, and the skip field design itself must allow for 0 one-time complexity ++ and -— operations. So my specific implementation of this at the moment uses what I call a chain group allocation pattern, but you could also call it a doubly linked intrusive list of nodes. I prefer not to use the term nodes or linked list because when I think about that, I think about singular elements rather than collections, but it doesn't actually matter. It's all just nomenclature. These contain memory blocks, block metadata, and skip fields. I use PLF stack, which is my own stack implementation for recording and reusing erased element locations. And I've developed basically a generic numeric pattern called a jump counting skip field, which enables 0 one-time complexity iterator operations. So I'll go into each of those very briefly. So the good thing about having a sort of linked list kind of format for memory blocks as opposed to something like a vector of pointers or whatever, is that it makes releasing the memory blocks very quick. You don't get that reallocation cost, and you don't get any pointer problems. For example, if you're doing a vector of memory blocks rather than pointers to memory blocks. It has a growth factor of 2, but you could use anything typically. And the minimum and maximum group sizes are customizable. So for example, if you knew the size of your cache and you knew the size of your elements, then you could set your minimum and maximum sizes to the same amount and have them fit into the cache a little bit better or whatever. PLF stack, it's basically just a faster stack implementation. So faster than any standard library container in stack context for non-scalar types and for large numbers of scalar types, regardless of compiler, and that includes vector and dec, of course. The performance advantage over the standard library components increases with the size of the element being stored. Also uses that chain group allocation pattern. Minimum and maximum group sizes are also customizable. So for all of the benchmarks that I'm going to be presenting today, vertical scale is duration in microseconds, less is better. Horizontal scale is number of elements in the container. So here we're comparing PLF stack versus standard vector versus standard stack under GCC. This is total time, so this time to push all of the elements into the container and then pop them all off and read each of them. Also, for all of the tests that I'm doing today, I'm just using small structs. If you want to see results for scalar types or large structs, go to the website, although I need to update the benchmarks on there because they're a bit dated. They're from the beginning of the year. This is GCC 5 on the same platform, same OS. This is MSVC 2015. So PLF stack performance doesn't change much. The other ones, quite a bit. So for the rest of the test, I'm going to be using GCC. So how does it get used in Colony? Basically, when something gets erased, the memory location for that element gets pushed onto the stack. The next time the Colony has an insertion happen, it checks the stack. If the stack is empty, then it just inserts to the back of the Colony. If it's not empty, then it pops a location off the stack and it reuses it. Hence, the container is unordered, because you don't know where in the container that element that you insert is going to end up. So, now I'm just going to go into jump counting skip field pattern, but before I do that, I have to describe why I can't use a Boolean skip field instead of something else, because Boolean skip fields are kind of convenient and simple. The main problem in terms of the standard is that if you're using a Boolean skip field, then it makes your iteration time complexity random. So if you imagine you've got your skip field 00111, 000, 11111, whatever, between any two non-erased elements, you don't actually know in advance how many erased elements there's going to be in between them. And that means that when you go plus plus, it might have 50 skip field nodes that it needs to check before it finds the next non-erased element, or it might have 1, or it might have 0, etc. So the standard says we can't have that, we have to have 0, 1 operations on our iterators, so can't do that. But the actual real problem with it is that each of those checks on each of those Boolean nodes is a branching op. So depending on how many erasures you have, you can have very good performance or you can have really, really bad performance. And it makes your code entirely dependent on CPU branch prediction. And the other thing, of course, is that generally when we're doing a Boolean skip field, unless we're getting really specialized, we don't tend to do a bit field because bit fields are slower than byte level addressing. So we end up wasting memory as well. So jump counting skip field pattern counts the jumps, i.e. the number of consecutive erased elements. The updating of the field in terms of the mathematics, and the programming is very efficient. There's no branching code for the iteration. So the iteration code becomes a lot simpler. The erasure and insertion code becomes a little bit more complex. So this allows for time complexity 01 operations on your iterator. We're going to go into it a little bit, but we don't have a couple of hours for me to totally bore you. So if you want to know like the entire algorithms and the whole thing, there's a 7,000 word paper on my website. You can go there and read through it, and I promise you by the end of it, you will be thoroughly bored. So just a little bit of benchmarking. So this is comparing PLF colony using a jump counting skip field versus that vector workaround with the Boolean skip field that we talked about earlier, versus a colony using a Boolean skip field. So this is prior to any erasures happening in the container. And you can see that vector is doing a little better. The Boolean colony is doing a little bit worse. So let's erase 25% of all of the elements in the container randomly and see what happens to the iteration speed. So suddenly colony is doing a little bit better, and the two Boolean implementations are doing much worse. So let's jump that up to 50% of all elements in the container are erased at random. Unsurprisingly, the other two get worse again. Now let's go up to 75%. Somewhat surprisingly, the other two do better in this context than they did at 50%. Would anybody like to hazard a guess why? Yeah, exactly. So if we go back a little bit, at 0% erasures, all of these skip fields are just a bunch of zeros, so the CPU branch prediction works perfectly, and the Boolean implementations can actually do pretty darn well. Once you get up to 25% erasures, then basically you've got a 1 in 4 chance of a cache miss. At 50%, basically the branch prediction can't work at all because it's just getting a completely random stream of zeros and ones. And at 75%, you go back to having 1 in 4 chance of a cache miss again. So that's basically why Boolean skip fields suck. So comparison between jump counting skip field format and Boolean skip field. So basically the equivalent jump counting skip field is on the right. First thing you'll notice is that singular erasures are exactly the same. They stay as ones. Once you've got a couple in the row, they become 2, 2. Once you get more than that, you get this sort of increment by 1 notation where the first number describes how many consecutive erasures there are. So does the last number, and in between you get a 2, 3 or 2, 3, 4 or what have you, depending on the size of the skip field block. So I'm just using the term skip field block to refer to a number of consecutive erased elements. How's this useful? Okay, so for a Boolean skip field, it has to check every single field. For the jump counting skip field, it goes 003, jump 3, 004, jump 4, etc. Obviously, if you're going in reverse, then you're doing exactly the same thing. And you might be asking, well, that's fine, but what about the 2, 3 in the middle there? What's that useful for? That comes into play when you're reinserting back into the colony later on. Earlier I talked about you push the location to the stack and pop it back off and reuse it. That's what that's for, but I'll get into that in a bit. So comparison of iteration code. So in this context, we're looking at the skip field being separate to the memory block for the elements, which may not be implemented that way in all cases, but just for the sake of argument, we're doing it that way in this case. So you have your pointer to your element and your pointer to the skip field node associated with that element. And if you're doing a Boolean skip field, then you just increment both of those, check the skip field node, and if it's 1, then you loop it again, loop again, until such point as you reach a non-erased element. For the jump counting skip field, you do the same thing. You add 1 to the element pointer and the skip field pointer, and then you just add the value at the skip field node to both the element pointer and the skip field pointer. So there's no branching. So erasure from the jump counting skip field. In this case, where the arrow is basically to denote the skip field node associated with the element which we want to erase. So the first thing that we have to do is check the nodes to the left and the right of the skip field node. And basically there's 4 cases which resolve down to a single switch statement. If both of the left-hand and the right-hand node are 0, then that means there's no consecutive erased elements. We just set the skip field node to 1. Second example, if only the left-hand node is non-zero, that means that we're at the end of a skip field block and we update the block on that basis. Similarly, for the third one, if only the right-hand node is non-zero, that means that we're at the beginning of a skip field block. We update the block on that basis. And if both are non-zero, that means we're in between 2 skip field blocks and we basically join the 2 blocks and update them on that basis. Similarly for reinsertion, so this is where we're popping a memory location off the stack and reusing it upon insertion. So in this case, the arrow corresponds to the skip field node associated with the memory location which we want to reuse. So if both left and right are 0, it's just a single erased element, no consecutive erasures, set it to 0. If only the left-hand node is non-zero, we're at the end of the block, we update the block on that basis. If the right one is non-zero, we're at the beginning of a block, updated on that basis. If both left and right are non-zero, this is where that increment by 1 notation comes into play. So in the bottom example there, the 3 indicates how far we are away to the left from the first non-erased element. And with that information, we can find the start of the skip field block. And when we know the start of the skip field block, we also know how many elements are in the skip field block, and we can split the skip field block on that basis and update into 2 blocks. Again, if you want to see all the boring math, look at the paper. So that's all very useful, and now you vaguely know how a colony works and all that jazz. How does it perform? So we're going to have a death match. Going to start with just raw performance, comparing against just standard library containers, and we're not going to worry about all of those pesky game requirements, like keeping all our links valid and that sort of jazz. So I haven't included some of the C++11 ones like unordered map because the performance difference wasn't that great. So I'm going to start with just inserting singly a whole bunch of times into each of the containers, measuring that. And that's just to measure sort of on-the-fly insertion performance. Then going to erase from each of the containers 25% of all elements at random. And then we're going to iterate over the data. So not terribly real world, but just... Okay, so insertion performance. Map, multiset, list, not doing so great. Vector doing okay. Colony and deck doing pretty well. Yeah, lib standard C++'s deck implementation is pretty good. So logarithmic scale, we see a little bit of a crunch there between 100 and 1000 elements. Vector starts to look all right, but for the rest of it, it's more or less deck and colony doing very well. So erasure performance, linear scale. Obviously, this isn't terribly useful. The 2 standing out there are deck and vector without using the remove if formulation. So we'll go to the logarithmic scale. So deck and vector without using remove if in this particular context, not very good. With remove if, more or less on a par with colony. Map and multiset don't do too well, and list does pretty well. Iteration performance. Here we see multiset, map, and list sucking wildly. The others are doing pretty well. So if we go to the logarithmic scale, colony is doing well, but not as well as deck or vector. And we see a pretty weird thing happening with list. And I inquired around on the GCC forums, and the general consensus was, and this was basically validated by further testing, because list iteration is essentially very simple, it's just follow this pointer. As long as all of your list data is in the cache, then that iteration speed can actually be very fast. But unfortunately, once you get competition for the cache, or once your data no longer entirely fits within the cache, then your performance starts to get quite bad. So the other tests I did were just increasing and decreasing the size of the element being stored, and that sort of lip goes up and down accordingly. So who won that round? Colony had good insertion, excellent erasure speed, reasonable iteration speed. Vector had poor insertion speed, poor erasure without remove if, good with remove if, and excellent iteration speed. Deck, pretty much the same as Vector, except not quite as good for iteration, and it has good insertion speed. So, whoops, skipped one. So next round, we're going to start worrying about those pesky game requirements. So here we're using those two vector workarounds that we talked about earlier, a vector with a Boolean skip field, and a index, vector of indexes referring to a vector of elements. We're going to do sort of a similar thing with deck. We're going to have a deck with a Boolean skip field and basically a deck of pointers referring to a deck of elements. And the reason we can do that with deck, whereas we can't with vector, is because deck doesn't invalidate pointers upon insertion. So same tests, insertion speed, obviously the vector one's not doing as well. Colony and pointer deck more or less neck and neck. And the Boolean deck is doing quite a bit better because essentially it's got less to insert. It's a lot simpler. Erasure speed, logarithmic scale. So again, without remove if, not so great. With remove if, deck, the index vector and pointer deck approach more or less on a par with Colony, depending on how many elements there are. And the Boolean deck and the Boolean vector approach both are the best simply because you're just flicking a bit, so much faster. Iteration speed, no surprises there. The Boolean approaches don't do so well after you've erased 25% of all the elements. Colony doing pretty well, but again, not as good as index vector or pointer deck. So we pretty much have the same winners for the second round, but we've just disqualified the Boolean workarounds, essentially. So up until this point, all of the tests have been, relatively non-real world, fairly what you'd see on online benchmarks and that sort of thing. So we're going to try doing a slightly more real world test. So we're going to take each of these containers and we're going to vaguely simulate 30 minutes of game time, so 108,000 frames, assuming 60 frames a second, which is somewhere halfway in between average gaming time for mobile and PC. We're going to basically iterate over the data in each of the containers for every frame, and at random during each minute, so each 3,600 frames, we're going to erase and insert at random 1% of all the elements in each of the containers. And then we're going to increase that to 5%, and then we're going to increase that to 10%. Now, this may not match all use cases, obviously. Some games have much less things coming into play and being erased or whatever. Some of them have more. But it really depends on the kind of type of game that you've got. So this is just the total time taken, so the total duration time to simulate that half an hour of game time. So we see here with 1% modification, Colony not really doing so well. It's got a little bit of a bump there in the middle, which I haven't quite worked out yet, but I am going to. We can also see that the remove if variants aren't doing so well, which is fairly obvious because basically we've either got 1 or 0 erasures happening per frame, generally speaking. Let's see what's happening with memory. So we can see that Colony is doing a bit better than the vector approach, but not by that much. But it's more or less on a par with pointer deck in terms of memory usage. So at 1% modification per minute, probably not going to look at Colony, at least not for half an hour of gameplay. So let's bump it up to 5% modification. So suddenly we see beyond a certain number of elements, the other implementations of container workarounds start to suffer a little bit. This colony stays pretty much consistent. And what's happening in memory is at this point, because the vector and dec implementations can't actually erase from their containers or free up their data without invalidating pointers or indexes. So they've just got insertions happening, erasures happening, and the containers are just gradually growing. So at 5%, both of those implementations are using twice as much memory as Colony, and that's consistent. This is the logarithmic scale. That's consistent all the way back, regardless of however many elements you've got in your container. After half an hour, Colony is going to be using half as much memory just because of that element location recycling and the freeing up of blocks. So jumping up to 10%, you can see that the other containers start getting even more wildly out of scope in terms of performance. And you can anticipate that the longer you run this simulation for, that sort of lip that you get there will go further and further back down the number of elements. Memory, so at 10% modification, the other two are basically using 4 times as much memory. So that's kind of vaguely interesting. So it looks like Colony seems to be better for higher modification scenarios, and it seems to be doing better and better based on the amount of modification that you've got, at least compared to those 2 vector and dec modifications. So let's do an even more extreme example. Let's erase and insert a certain number of elements per frame instead of per minute, which sounds, I don't know, a little bit extreme, but when you think about something like bullets, you know, you can have 100 or maybe even 500 for a more bigger bullets flying out per second, and then 1 minute, or no, not 1 minute, 1 second or 2 seconds later, most of them have disappeared or lodged into something or gone off the game map or whatever. Also, quad tree, octree nodes, you get a lot of modification per frame, and outside of games, you can look like heavy modification scenarios like cellular or atomic simulation, that sort of thing. So, starting off with 1%, and we're going to use a much shorter time frame, just of 1 minute of game time, so 3,600 frames. So this is logarithmic scale because the linear scale kind of looks like that, where Colony is at the bottom and the other ones are up like that. So with this really high modification rate, Colony is basically around about a factor of 10 faster than the other ones. And we can see here that because obviously we've got a lot more erasures happening per frame, the remove if variants are doing quite a bit better as well. Bump it up to 5%, Colony does better again, and 10% better again. In terms of the memory usage at that point, so for 1% modification per frame, Colony is using 34 times less than the other two. 5% is using 172 times less after 1 minute. And at 10% it's using 340 times less memory after 1 minute of simulation, which is why I can't run this simulation for more than a minute, because if I run it for half an hour, it uses more memory than my computer has. So, bottom line, what is Colony vaguely useful for? Basically, high modification scenarios. So, if you've got a scenario where you haven't got too much modification going on, maybe you've got 1 or 2 erasures and insertions here and there over the course of half an hour, you probably wouldn't be reaching for Colony. But if you've got more than 1% erasures or insertions happening per 3,600 iterations over your data, that's when you would use it. So medium to high modification scenarios. If you've got less than that, if you've got less than 2% of your elements being inserted or erased, maybe you want to look at one of these dec or vector approaches. But whatever you do, you probably don't want to be using Boolean skip fields in general. So generally speaking, the higher the ratio of modification to iteration, the greater the performance and memory saving you get out of using Colony. And that's pretty much it for Colony, more or less. But the title of the talk was Colonies, Performance, and Why You Should Care. I've gone into Colonies, I've gone into performance, I haven't really gone into why you should care. And this is just a generalized statement about thinking about performance in computing, going back to what I was saying at the start. And I think it's fairly It's possible that over the next 10 to 20 years, we're going to see a fairly strong performance crunch in computing on the software side. There's a couple of reasons for that. Some of them are internal to computers, some of them are external. The internal reasons are we're kind of scraping the bottom of the barrel a lot of the time in terms of what we can get out of our hardware now, how much we can increase the performance. If you look at the 90s or whatever, we were more or less doubling CPU speeds every year or every couple of years, but that low-hanging fruit is gone. And now it's all down to, more efficient pipelining, cache, all that sort of jazz, and parallelizing, not parallelizing, where we can. But of course, parallelizing has a fairly limited scope to an extent. So we have to kind of look at things in a kind of context where this is sort of what we got, and we are going to get gradual performance increases, but short of a major sort of computing technology revolution, we're not going to get the kind of 200% performance increases that we were getting in the 90s. So we can't rely on hardware now to sort out all our performance problems for us. At the same time, externally in the real world, people are obviously using computers more and more. They're demanding more from them, and they're doing more with them. If you look at the 90s, again, everybody was doing everything still on paper, still on faxes, whatever. Now everything's transitioned to digital documents, media, communication. Why? Because it's essentially more efficient. And the other thing that's going to drive that efficiency, I think, economically, is basically sheer sort of population numbers, that sort of thing. We've got roughly double the number of people on the planet there were when I was born. At the same time, we have some diminishing natural resources, that sort of jazz. I mentioned Google Maps earlier. That's a good example of using computing technology to greatly increase our real-world efficiency and use of resources. And I think we're going to need a lot more of that over the coming years. And I think at the front of that performance crunch is probably going to be C++ in terms of programming, because we don't really have anything else that accesses that high level of abstraction and the low level of abstraction at the same time. And that low level is really important for being able to modify for different hardware scenarios, getting access to registers, all that sort of jazz. But we're going to have to look at a lot of change in the language and in the way that we do computing. And some of that change is going to be hard won, because now I imagine whoever wrote this quote was kind of pissed off at academics, but it more or less applies to any scenario where you've got a knowledge field which has got a great level of complexity in it. And I don't think anybody would argue against the fact that C++ at this point has a great level of complexity. And the problem with that is that the kinds of minds that come towards programming tend to be very intelligent, and we tend to get very wrapped up in ourselves in terms of thinking of ourselves as knowing a lot, this sort of jazz, and I'm not discluding myself from that at all. I'm just as bad. The only problem with that is that once you know a lot, then when what you know changes, there tends to be some resistance to change. And we're already seeing a bit of that with SG14 and various other movements that are happening. So my last point with that is simply to say that I think it behooves us all, including myself, to look at the ways that we are holding ourselves back in terms of the computing industry and in terms of C++ and the way we program and that sort of thing. And that's all I've got. Any questions? Yeah, so questions? Yep.
Do you intend to submit this to the standard?
Sorry?
Do you intend to submit this to the standard?
Eventually, yeah. I want to get it into Boost first if I can. The main problem for that is basically finding the time to work on the documentation and get it into the Boost format. I think once it's gone through that process, then I'll be in a better sort of position to write something up in terms of a proposal. I think the biggest problem with that is really going to be separating out what makes a colony from an abstract point of view versus an implementation point of view. So yeah, but eventually. At the moment, it's just sort of free form for whoever wants to use it and modify it and whatnot. So yeah.
When you modify the skip field structure, sometimes you have to redo an entire block. Is that right?
Yeah.
Have you measured how big do they get?
Yeah. So the question was, when you modify the skip field structure, in rare instances, you might have to update the skip field for the entire block. For example, if all of the elements in the skip field, if all of the elements in that particular block have been erased but one or two, depending on where the elements that you're erasing are, then you could be updating a whole lot of the block. I thought this would be problematic, but in terms of actual implementation, it turns out that it's not. And the reason for that is, again, there's no real branching happening. But the other thing is that, like I said earlier, when you have these blocks and they become empty, they get freed to the OS. So that takes out a lot of those sort of big, long strings of erased elements. And the other thing, in terms of my implementation of Colony, basically I've got a 16-bit unsigned int skip field, and so the block sizes are limited at max to 65535 elements. And that just limits the amount of that kind of skip field update factor. So, you know, you could imagine if you had unlimited block size, if it went up to 64-bit size or whatever, then you could end up having to update huge amounts of skip field nodes for a given erasure. But keeping those block sizes smaller, but still not too small, because remember we're talking about games, we're not talking about huge number of objects. It just cuts down on what the performance cost of that is. And in terms of the benchmarking that I've done, at least, I haven't found that to be a significantly, detrimental factor. Yeah. Yes.
Are there any other problem domains you're aware of that would benefit from these techniques?
So the question was, are there any other problem domains that would benefit from these techniques? I think any problem domain where you're using, for whatever reason, a Boolean skip field, binary skip field, or an equivalent, you definitely benefit from at least looking into the jump counting skip field pattern and seeing whether that would fit into that scenario, taking into account that kind of block size thing that I talked about earlier. In terms of the other stuff, I'm not so familiar with other domains, but basically any domain which has unordered data, which is modified significantly, and where the ratio skews towards reasonable amount of iteration and a reasonable amount of modification, then you're going to get some performance benefit from using a colony. Yeah. Anybody else? Yes?
How many bits each element in skip list takes?
Sorry, could you say that again?
How many bits does each element in skip list takes?
In what? Oh, in the skip field.
Yeah.
Yeah, 16-bit for my implementation. But actually,
Whole skip list or each element? One.
each element. So it adds 16-bit int for unsigned int for each element, basically.
So there should be as much skip list elements as the object elements.
Yeah, ideally. So the general question was how much memory wastage do you get from having that jump counting skip field there? And in terms of my implementation, 16-bit, but actually I just remembered it's part of the template. You can change the size of the skip field, which also, the skip field unsigned int type, which also changes the maximum size of each of the memory blocks. So for example, if you only had, you were only thinking about having maybe 200 to 400 elements, then you might want to change it to a uint 8 type instead of a uint 16. And then you only get, a byte wastage per element. So ideally in terms of what you're storing, you're going to be better off storing something that's larger than a 16-bit integer, but it just depends what you're doing. Again, for the gaming scenario, we're looking at structs and classes, so pretty much everything is larger than a 16-bit int, so, or most things. Yeah. Anybody else? Yep. Totally couldn't hear that, sorry.
How does Colony behave in a concurrent environment?
I do not know. The question is, how does Colony behave in a concurrent environment? I would really like to know that. I would really like somebody to step up and kind of go, hey, I'm going to take Colony, I'm going to make a multi-threaded version of it. At the current point in time, the thread-safe guarantees are basically the same as the standard library. So, concurrent reads are fine, concurrent writes, not so much. I'm not sure what the performance differences would be in a concurrent environment, but I would be very interested to know. Yeah. Anybody else? No, looks like we're done. Thank you very much.